Welcome back to another video, guys. I got this POV math camera again. This is gonna be another Let's Learn Computer Science, continuing our discrete math course. Today we're going to be talking about recurrence relations and induction methods and recursive structures. So I'm going to switch over to my other display here to show you some of the problems that we have. So given the recurrence relation a(n plus 1 equals 3a sub n minus 2a sub n minus 1, and initial values a of 0 equals 0 and a sub 1 equals 1, what is a sub 5? So this one isn't having us do any induction necessarily, it's just asking us to plug in values into this formula and grab stuff from there. Alright, just had to fix the camera there, make the pen show up a little bit tighter. So this should be pretty simple. So we're given 0 and 1, so from that we're able to calculate 2. So let's say I'm solving for a sub 2, that would be equal to n plus 1, that means a sub n is 1, this one. And then I'm going to subtract 2 times a n minus 1. Since n plus 1 was 2, n minus 1 is 0. And a sub 0 is equal to 0. So here we can see a sub 2 is equal to 3. That means a sub 3 will be equal to 3 times 3 minus 2 times 1. And this will be equal to 9 minus 2, which is 7. That means a sub 4 will equal 3 times 7 minus 2 times 3. This will equal a sub 4, so this is 21 minus 6, which is 15. And finally, a sub 5 is going to be 3 times 15 minus 2 times 7. Oh, that's a 15. So this will equal 45 minus 14, and that gives us 31. So a sub 5 is equal to 31. Alright, we're shifting gears here and getting into an induction proof, a proof by induction problem. So for the following questions, we need to figure out the base case for the induction proof, we need to figure out the induction hypothesis, and then we need to figure out what needs to be proved to complete the induction step, and for an extra challenge, we will complete the proof. I'll probably complete the proof on all these. So let's go through this. We're given the series 11 plus 19 plus 27 plus dot 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 plus 8n plus 3, and that is equal to n times 4n plus 7. I have that right? Yes. So I'm going to call this value S. I'm going to call this series S. And what I can do from there is establish our base case. So my base case will just be plugging in 1 into the equation that gives me a sub 1. So this gives me the sum of the series, right? But if I just want to find one term in the series, I use this equation. So I can do 8 times 1, my n is equal to 1, and then add 3, and this gets me 11. So this is true. A sub 1 is 11, and this is called our base case. So next I need to establish my induction hypothesis, and our hypothesis would look something like, it's basically what was given is our hypothesis, but I'm just going to write it slightly differently in a summation form. So let's say summation starting from n equals 1 to some positive integer k. I want to say that 8n plus 3 is equal to n times 4n plus 7. So this is my hypothesis. Induction hypothesis. So finally I want to show what is the step that I must prove, what is the equality I must prove in order to prove that this is true, that my hypothesis is true? Well, the way induction works is you start with a base case, and then you try to prove that any successive cases are true. So if a sub 1, then we can figure out a sub 2. And if we can figure out a sub 2, then we can figure out a sub 3. And it goes successively like that. So it's kind of like, if I can figure out n, then I can figure out n plus 1. Then I'm going to treat this n plus 1 as my new n value, and from there I can figure out n plus 1, because I just proved that I could through this step. So it's going to be that all the way down. So let's plug in n plus 1 into here and see what we can do with that. So what I'm going to do is write n equals 1 k plus 1 of 8n plus 3. So I want to find a representation of this as a sum. Okay. So what I can do is refactor this in terms that we're familiar with, right? I want to utilize my induction hypothesis in order to prove this. So the way I can do that is I can decrease this upper term by 1 by k. And these aren't equal anymore. In order to make them equal, I would need to add that last term, which is this k plus 1 term. So I'm going to say plus 8 k plus 1 plus 3. So here I'm manually adding that last term so that both of these are equal. And I do it this way because my induction hypothesis has a definition for this exact term. And I can use substitution to pop it in. So let's do just that. I have n times 4n plus 3 plus 8 times k plus 1 plus 3. Oh, this is a 7. Okay. N times 4n plus 7 plus 8 times k plus 1 plus 3. Let's make all these variables k for the sake of simplification. So now let's simplify this out. Let's say 4k squared plus 7k, and then plus 8k plus 8 plus 3. Right, I've just distributed out all of those, and now I'm going to simplify. I get 4k squared plus 15k plus 11. And then let's try to factor this. Let's do 4k plus and k plus. Now 11's a prime, so one of these is going to have to be 11. If this one was 11, then it'd be 4 times 11, and that'd be 44, and that's way too much. It's way over 15. So I'm going to put 11 here, and then this one just becomes 1. So now I have this 4k plus 11 times k plus 1, and that is equal to this. So let's rewrite this in terms of s now. Let's say s plus 8k plus 1 plus 3 is equal to 4k plus 11 times k plus 11, or k plus 1. And then the last thing we could do to confirm that this is true is plug in n plus 1 into our hypothesis. Right, so let's substitute each of these n values with an n plus 1. Let's do n plus 1 times 4 times n plus 1 plus 7. Multiply this out. That'll get me n plus 1 times 4n plus 4 plus 7. And that will equal 4n plus 11 times n plus 1. And as you can see, this is going to be the same as this. And that is our proof by induction completed. So let's move on to this next proof by induction. It asks, for all natural numbers n, 3 evenly divides 7 to the n minus 4 to the n. Now this is going to be a different strategy with proof by induction. This is going to be called a divisibility proof by induction, where we're not given necessarily a series, nothing's being added together, we just want to see if the difference between these two values is a multiple of 3. So how can I express that? I want to say 7 to the power of n minus 4 to the power of n is going to be equal to 3 times some integer, let's call it m. So this would be my induction hypothesis, if I'm trying to prove that this statement is true. And I'd set up a base case. So if I do 7 to the power of 1 minus 4 to the power of 1, that's equal to 7 minus 4 is 3. So that works. That is our base case. So I know that's true if n is a value of 1. Now I want to see if it's true for 7 to the power of n plus 1 minus 4 to the power of n plus 1. And I need that to equal 3m. Maybe not m, maybe we'll call this p. So it needs to equal some multiple of 3 times some integer. So how can we start to solve this? This is what needs to be proved. Prove this. So the first thing that catches my eye is I can split this 7 into its individual powers. So I could do 7 to the first times 7 to the power of n, because exponents have this relationship. And I can do the same thing over here. Times 4 to the n. And now I can do something interesting. I can factor this to get an equation that looks more like this. So in order to do that, let's say 7 to the n minus 4 to the n times 7. And then I'll do a plus sign here to do 4 times 7 to the n minus 4 to the n. Let's make sure this works. So that'd be 7 plus 1 minus 7 times 4 to the n. And this would be plus 4 times 7 to the n minus 4 to the n plus 1. That doesn't seem to work out. Let's see if I can do this differently. I want 7 times 4 to the n, a minus on this side and a plus on this side. So that probably needs to be 4 to the n, and this just needs to be 7. So let's do 7 to the n minus 4 to the n times 7 plus 4 to the n times 7, and then this would just need to be 4. So if I do it that way, this will be 3, but I don't want to simplify that yet, because when I go here, that's 7 to the n plus 1. This is 4 to the n plus 1. And then these two terms would cancel out when they get multiplied. So I want to keep it in that form. And now I can plug in my induction hypothesis. So let's do that. 3m times 7 plus 4n times 7 minus 4. Simplify this to be 3 times 7m, let's call it, and then plus 3 times 4 to the n. Then I want to factor out a 3 and get 7m plus 4 to the n. And now you can see I've solved this equation in terms of some multiple of 3. I was able to substitute values to get some multiple of 3. So that's me proving this, where p is equal to 7 times m plus 4 to the power of n. So there we go. I can conclude this by saying that 3 evenly divides 7 to the power of n minus 4 to the power of n for all n included in, not that. The set of all natural numbers, not the negatives. Alright guys, we're going to finish up with this last induction problem. For all integers n larger than 2, the following inequality holds. 2 to the power of n is larger than 2 times n. Now, this may seem like common sense to a lot of people. Obviously, if we related them as a function, if we graphed both of these, we could very clearly see that this exponential function grows, well, exponentially larger than this linear function. But we can also prove it by induction. So let's go through starting that here. Let's do our hypothesis. 2 to the power of n is greater than 2 times n. So that's our hypothesis. Let's set up a base case. It did specify, okay, maybe I should say that, for n greater than or equal to 3. So I need to be greater than 2. So when we have an inequality like this, or a restriction on what our value of n can be, this determines what our base case will be. So here I want to pick the lowest value, which is going to be 3. So for n equals 3, 2 to the power of n is equal to 8, and 2 times n is equal to 6. 8 is greater than 6. That is an okay base case. So now I want to prove something. I want to prove by my induction step. I want to prove that 2 to the power of n plus 1 is greater than 2 times n plus 1. This is what I want to prove. So how can I go about that? Well, as you've seen from the previous 2 questions, we're probably going to use our hypothesis. So I need to find somewhere to substitute this, and I can see exactly where I'm going to do that. I'm going to split this up just like the previous question into 2 to the power of 1 times 2 to the power of k. I'm going to be using k now. And that is greater than 2 times k plus 1, or plus 2. So usually once you're getting into the actual induction process, you're using k, but for everything else, you're going to be using n. And maybe for this induction step, you'd introduce k. You'd say, assume for some value k. Yeah. Because you don't want to conflate things from your hypothesis with this or your base case. So now that I have this set up, I can relate that to my hypothesis, which was 2n is greater than 2 times n. Well, if I multiply both sides by 2, this side looks a heck of a lot like this side, doesn't it? So I'm going to substitute that in. 2 times 2 to the power of k is greater than 4 times k. So in this induction step, while using my hypothesis, I have this relationship where 2 times k plus 1 is greater than 2k plus 2, and 2 to the power of k plus 1 is greater than 4k. But I need to figure out the relationship between these two. Is this one greater? Is this one greater? How can we figure that out? So I'm going to set up an inequality of 4k is greater than 2k plus 2. Right, this is my assumption. This is what I'm trying to prove now. I'm going to go ahead and subtract 2k from both sides. This simplifies to 2k is greater than 2. Then I'm going to divide by 2 on both sides, and I get k is greater than 1. So it looks like 4k is greater than 2k plus 2 if and only if k is greater than 1. Well, based on my restriction of what n can be, k will always be greater than 1. It'll be greater than 2 always. So I can finish up this relationship by saying 2 to the power of k plus 1 is going to be greater than 4k, and 4k is greater than 2k plus 2. So here we can see by proof of induction, 2 to the power of k plus 1 is in fact greater than 2k plus 2 using the hypothesis. The hypothesis defines this to be true, and the hypothesis plus our induction step assumption proves this to be true, and the whole thing. So there we go. Thanks for watching today's video. Feel free to leave a comment. Tell me what you want to see next. Peace.